So now, let's talk about the difference between mass and weight. Mass and weight. Continuation from our Newton's laws of motion. Now, we always talk about matter. We say matter is anything that has mass and occupies space. And we're told that we have 3 states of matter. Matter is solid, liquid, gas. And now we have the 4th state called the plasma state, which is a superheated gas state. But now, that's not the bone of contention. We have mass. And mass itself is just the quantity of matter contained in a body. So that quantity of matter a body contains is mass. So number 1 for mass. Mass is the quantity of matter contained in a body. 2 for weight. Weight is the earth pull on a body. A body that has mass, immediately gravity acts on that body. The body will now have what we call weight. So mass is different from weight. It is the mass that gravity has acted on that gives weight. So when gravity acts on a certain mass of a body, then the body now have what we call weight. So weight is the earth pull on the body. Let's see 2 for mass. Mass does not vary at any point on the earth's surface. If you take the mass of a body, if you measure the mass of a body as 200 grams in Accra, Ghana, it will be 200 grams. If you take the same mass of that body to Istanbul, Turkey, it will still be 200 grams. If you measure it as 200 grams in Lagos, if you take it out there in Abuja, it will still be 200 grams. So wherever you take it to, it will not change. Mass of bodies don't change. They are like that everywhere you take them to. If you take that same mass of body to the outer space, it's still the same body. It will not change. The only time it will change is if there is a change of state, meaning moving from one state of matter to another. That's only when you see mass change. But if there is no change of state, mass of a body remains the way it is. It does not vary at any point on the Earth's surface. Now, but weight of a body slightly varies at different points on the Earth's surface. Now, it's because of the variance of the mass of weight. That's the reason we discovered that, wonderful. Christopher Columbus said he traveled around the whole world. Let's assume so. Probably 75 to 80% of the earth through water. And he said that the earth was spherical in shape. He explained that in geographical science. And, well, check some of the principles of viscous and merry-go. Good. Check Kepler's. Wonderful. But from modern day physics, we discovered that the earth to a geographer is spherical, but to a physicist, this principle here, weight, make us understand that it is not perfectly spherical. It has something we call an elliptical shape or a geoid shape. It has an elliptical or a geoid shape. Now, if you take if the earth is spherical, for example, applying my own basics, if I take a body, this is north, this is south, this is east, and I believe this should be west, and it's perfectly spherical. The center of gravity of a body acts here. center of gravity, CJ of a body, or CJ of the body acting. This is the Earth, and the CJ of the Earth will act at the center of the Earth. Good. If I take a body of mass 20 grams to this part of the Earth, the weight of the body will be times 10, and it will give me 200 Newton. If I take it down here, it will be 200 Newton. If I take it here, it will be 200 Newton. And if I take it here, it will be 200 Newton. This situation is only setting if the Earth was actually perfectly spherical. But experiments have shown that if you take bodies to this part of the Earth at the north, it gives you maybe 19.6 Newton, and when you take it here, it gives you about 19.73 Newton. But when you take it here, it can weigh up to maybe 24.11, maybe somehow, maybe you have about 15.7 Newton, and you take it here, it weighs about 15.2 Newton. What it means is that these parts that weigh higher, 19.6, 19.6, if they weigh higher because they are closer to the center, that's why they weigh higher. They are closer to the center of gravity, so they weigh higher. But these ones that are farther away from the center, they weigh lower. The closer they are to the center of gravity, the higher the center of gravity on them. And the higher the center of gravity on them, on that body of mass, the higher the weight of the body. Because weight is the earth pull on the body. So because of that, it shows that the earth actually does not have this spherical shape. This is the shape of the earth. So this shows that this is north, south, east, and west. So what it means is that the north and the south is closer to the center of gravity than the west and the east. So bodies taken to the west and the east will surely weigh lower because they are farther away from gravity. But the bodies at north and south will weigh higher because they are closer to this center of gravity. So the earth does not have a spherical shape to a physicist. It has an elliptical or a judge shape. But to a geographist, probably that's the earth, perfectly spherical. So the weight is earth pull 2. It varies at different points on the earth's surface. So if you weigh bodies at different points of the earth's surface, they have tendency of varying because the earth is elliptical or judge in shape. Good. So the third one on for mass is measured in kilogram. It's measured in kilogram. That's its kg. And weight is measured in Newton. That's another difference between them. So for the fourth one for mass is that it's measured basically with a beam balance. You've heard of something called a beam balance, a chemical balance, a beam balance. Use it to measure mass. But why for weight, the basic thing used for measure weight is the spring balance. In the laboratory, it gives you an exact value of the weight of your body. Good. So, but the two of them are related with the formula that weight is equals to mass times gravity. So, weight is mg. Always remember this formula. Weight is mg. So, m is mass, g is gravity, and w stands for weight of a body. Now, we're done with that. We'll progress to the next stage of Newton's laws of motion. Let's talk about bodies in an elevator. Okay. body in an elevator. Or sometimes people say it's a lift. An elevator, a lift. Good. Now, when if your first time of entering an elevator, you have tendency of, by the time the button is pressed on the wall, you just observe that some of you'll be holding the wall or trying to hold the next person by your side. You are good. It's not your fault. It's just that it's a physical principle that causes that to happen. Now, if you look at a body inside an elevator, there are two forces that act on that body. That body experiences two forces. Let's assume this is the body inside the elevator. Okay, good. I'm very good at drawing. Very good at drawing. So you have this. You have this. You have this. Okay. Let's put on a shoe. Put another shoe here. Understand probably with eyes, mouth, and nose. Wonderful. So when you have something like this, no. Fingers is 5. 5 fingers. Good. So now, for every action, there should be an opposite reaction. So the weight of the body is acting down, which is mg. That's mg. The weight of the body is acting down, mg. But there is another force that is acting upward. It's called the reaction force, R, and it's also mg. For every action, there's equal and opposite reaction. Now, the body has tendency of moving up or down. Elevators can either move upward or go down. So, I will put this, my arrows will be on both directions. That will be acceleration in meter per second square. So, it can either move upward or downward. That's an elevator. So, but first of all, we're going to consider 3 situations. The first one is a situation where the body is moving upward. The situation when it's moving downward. So let's consider when the body is moving upward. So first of all, when it's moving upwards, the tension T is given as T. That's the tension you experience. The resultant force you experience is the tension. Now, it's equals to the weight. And it's equal to A plus G. Depends on how you can just take the tension directly. So the tension is equal to M is equal to. So take note of this when the body is moving upward. But in a situation where when the body is moving down, something has happened. The tension T is given as T is equals to M into bracket G minus A. Please take note of these two. So 2 situations are one when the body is moving upward, and 2 when the body is moving downward. So when the body is moving upward, you have the mass of the body, A plus G. And when the body is moving downward, mass of the body, G minus A. But there are situations, a situation where the body begins to move downwards. As the body is moving downward, it's going downward. At a certain point, it's moving downward with a very high speed. You see, when an elevator is moving at a very high speed, somebody who is not used to that kind of tension, that person, you see the person, you'll be scared. You see fear. You'll be looking for something to hold. He will feel some kind of emptiness within himself. Now, this is the reason. When a body is falling with that acceleration, it's coming down in an elevator. A certain point is reached. That's the third stage. That certain point is reached where, that's when a point is reached at A equals to G, or G greater than A. That's when either acceleration at which is going down, this acceleration at which is going down, becomes equal to G or less than G, meaning G is now greater than it. Something will happen. The tension will now be equals to M into bracket G minus A. From here becomes A is now equals to G, becomes G. So what happened? Become M into bracket G into bracket 0. So what happened? M times 0 becomes 0. So the body will experience something when the tension on it is 0. The tension on it is 0, the weight of the body, everything is 0. The body will experience something called weightlessness. The body will experience weightlessness. That's when you start seeing, it looks as if you don't have weight. It looks like you are going down as if, and sometimes you experience that fall, you feel empty, feel as if you are, but when you are used to an elevator, you know that's how it's a normal thing. But when you are not used to it, you get scared. So the reason is because of T is M is G minus A, M at a point when A is equal to G. So when you just replace it into the formula, what you get is 0. But sometimes G can be greater than A. G greater than A meaning it's not going to be even 0. It's going to be less than 0, which is become what? Minus. And at that point, you have reached a point where you start floating because you are completely weightless. So that is the principle of a body in an elevator. Now, let's talk about the third law of motion, which is Newton's third law of motion. The third law of motion is simple. It states that for every action, there is equal and opposite reaction. If you decide to slap the wall with your hand, the force you exert on the wall is equal to the force the wall exerts back on your hand. So that's why you feel pain in your hand. So if a bike collides with a car, the bike gets damaged, the car will get damaged, because for every action there is equal and opposite reaction. So when you ask, state the third law of motion, it states that for every action there is equal and opposite reaction, or simply you just say force and reaction are equal. Simple. Now that's that. Now what are the consequences of this third law? The first consequence about this third law is that if you take a look at the aeroplane, for example, or something like the rockets, when they are flying, there is this air that comes out of their nozzle. There's this air, this thing that comes out. Some of you say smoke. It's gas of air that comes out with a very high speed from their nozzles. The movement of those gas is moving backward. So as the movement of that gas is moving backward, it's causing a resultant effect. For every action, there is equal and opposite reaction. That backward force that gas is causing to move backward, so also is causing a resultant reaction on the aeroplane to cause that aeroplane to move forward. Hence, the aeroplane can move forward as the gas is moving backward. So for every action, there is equal and opposite reaction. So as a rocket escapes from the Earth's that gas comes out with a very high force from his nozzle, so also the head of the rocket tends to pierce higher and move further, because for every action there is equal and opposite reaction. That's one of the consequences of the third law of motion. The second consequence is when you shoot a bullet out of a gun, you observe that the person holding the gun, there's always this shake in his hand, this change in momentum in his hand. There's always this vibration that goes with shooting of bullets out of a gun. So if you shoot a bullet out of a gun, you experience a kind of backward force. That backward force has a name. It is called the recoil velocity or the recoil speed. It's a backward speed. So when you shoot a gun here, it moves. There is this backward movement. So I'll create a deduction for that. A deduction will go with it. And that deduction is, if a bullet of mass mb is shot out of a gun, of mass mg with a velocity vb, the gun is found to experience a backward velocity known as recoil velocity. Now, that is mass of gun, velocity of gun is equals to mass of bullet, velocity of bullet. Because for every action, there is equal and opposite reaction. Now, what is velocity of gun now, which is the recoil velocity of gun? That becomes mass of bullet, velocity of bullet, divided by mass of gun. So you can have this formula and keep it. So mass of gun, velocity of gun, mass of bullets, mass of gun, mass of bullet, velocity bullet, mass of gun is equals to velocity of gun, where Vg is recoil velocity of the gun. So put that out. Now, from there, we've seen these as the consequences. Now we can take something else. Let's talk about something we call conservation of linear momentum. It's a principle. It's a principle, conservation of linear momentum. But before that, we already know what momentum is all about. Momentum is mass times velocity. Good. So because we know that, let's see how linear momentum can be conserved. But basically, linear momentum being conserved has something, a lot to do with what we call collision. Now, principle of conservation of linear momentum. So that's it. Now, conservation of linear momentum is all about collision. And basically we have two types of collision. The first collision we have is called elastic collision. And the second one is inelastic collision. So collision can be elastic, collision can be inelastic. So we have elastic collision and we have inelastic collision. So when two bodies collide together and they bounce back, that is elastic. But when these two bodies collide and they stick together, then it is inelastic. For example, you take something like feces, shoot it towards the wall. What happens? It will paste to the wall like a paint. That is inelastic collision. If you take something that is sticky, you throw it towards a stationary object, it will stick to that object because it is inelastic. But when you throw something like a ball towards a wall, it hits the wall and bounces back. That is elastic collision. Or when you hit two balls together, they hit each other and they bounce. The reason is because that is elastic collision. Now this principle of conservation of linear momentum, simple. I'll state. It states that in a system of colliding bodies, the sum of the initial momentum must equal the sum of the final momentum. In a system of colliding bodies, sum of initial momentum equal sum of final momentum, provided no external force is applied. Let's take it again. In a system of colliding bodies, whether the system is elastic or inelastic, it doesn't matter. In a system of colliding bodies, the sum of the initial momentum must equal sum of the final momentum, provided no external force is applied. Good. Now, we already know that elastic and inelastic are the two forms of collision. Now we know that the principle of conservation of linear momentum states that in a system of colliding bodies, that the sum of the initial momentum must equal sum of final momentum, provided no external force is applied. Beautiful.